Dear students, today we will discuss the various examples related to the three types of statistics. First, we will summarize the three types of statistics. First, we will write the statistics. Next, we will write the thermodynamic probability. And then we will write the number of particles in the ith state. So the first statistical that is the Maxwell-Boltzmann statistics. Here the thermodynamic probability, which we represent by WMB, is equal to, we have already derived this, so we will summarize here, and factorial product of GI Ni upon Ni factorial, and the number of particles in the ith state will be equal to GI upon e raised power alpha plus beta ei. Here beta is equal to 1 upon kt. You have to remember for all the three statistics that this value of beta is equal to 1 upon kt, which we have already derived. So the next one is that is Bose-Einstein. Statistics. Here the thermodynamic probability is equal to pi I Ni plus Gi minus 1 whole factorial upon Ni factorial Gi minus 1 factorial, and the number of particles in the ith state is simply given by this expression Gi upon e raised power alpha plus beta ei minus 1. And the last one we have, that is Fermi-Dirac. staticus, which is given by this expression pi I gi factorial upon ni factorial gi minus ni factorial. Ni factorial will be equal to gi upon e raised power alpha plus beta ei here. So these are the three types of staticus which we have already discussed in the previous video lectures, and we have just summarized here the thermodynamic probability and number of particles in the ith state. One more point you have to remember here is that both Bose-Einstein and FD staticus they basically reduce to MB statistics. Very important. For the condition when we have this Ni is less than Gi, or you can say Gi is greater than. This is very important. For these conditions, these two statistics will simply reduce to MB statistics. Okay. First, we will see the question 1, how to solve it. Suppose we have a question: a system of n particles has among others two energy levels. With G1 is equal to 2 and G2 is equal to 3. E1 is also given, or you can say U1. The examples are in the previous lectures. You have represented the energy with the U1, so we will write that U1 here. So you can take it E1 also. So 41.84 kilojoule per mole, and U2 is equal to 58.58 kilojoule per mole. Now the question is, calculate the ratio of particles in the two energy states, and temperature is also given at 1000 Kelvin. Now we have to basically calculate the ratio of simply the particles. In the previous lecture we have done this equation that Ni upon Nj is equal to Gi upon Gj into e raised power minus Ei minus Ej upon Kt. So we will use this equation here. So it will imply, because it is given that energy E1 and here U1 and U2 also given, and G1 and G2 is also given. So we will transform this equation into, suppose N2 upon N1 will be equal to G2 upon G1 as per this equation, and E is nothing but it is simply exponential, and we will give it back. So it will be minus E2 minus E1 upon Kt. So this can also be written as G2 upon G1 exponential minus U2 minus U1 upon RT. What we have done, this is for one molecule, we have taken the 1 mole here, so it will be simply equal to G2 is given here. This is G2 is equal to 3 and G1 is equal to 2, so we will simply write 3 upon 2 exponential, and we will put the values. Five eight 580. We can change this into joule per mole here, and this also into joule per mole. Simply multiply by 1000 minus 4184. This is in joule per mole upon, I have to use this universal gas constant, so its value will be into joule per mole, 38.314 joule per Kelvin per mole. So, and simply multiplied by the temperature in Kelvin scale, that is also given here 1000. So we will multiply it here 1000. So first you have to solve this and take the exponential simply by using exponential function from the calculator, and you can calculate its value comes out to be 0.201. So this is how a question is solved based on the ratio of particles into energy status at a particular temperature. Now we will take second example here, which is telling us using the Stirling approximation calculate ln and a factorial, where Na is simply Avogadro number. Avogadro's number. So we have to simply use the Stirling approximation. Here we will first write Na is simply equal to, we can put the value 6.022 or 23 sometimes into 10 raised power 23. Now using Stirling approximation, we can write ln of Na factorial is equal to Na ln of Na minus Na. So we are using this simple approximation without using the other approximation. We will use only this approximation here and put simply the values here. 6.022 into 10 raised power 23 natural logarithm of 6.022 into 10 raised power 23 minus 6.022 into 10 raised power 23. So this comes out to be 3.238 into 10 raised power 25. Okay. Now we will take some of the questions basically asked in CSIR net. This was basically asked in December 2017. Question is, four distinguishable molecules are distributed in energy level E1 and E2 with degeneracy is also given. That means G of 2 and 3. That means for energy E1, G is equal to G1 is equal to 2 and G2 is equal to 3. Okay. So number of microstates with 3 molecules in energy level E1 and one in energy level E2. Yes. The options were, first option was 4, second was 12, third was 96, and the fourth was 192. So First you have to remember these are distinguishable molecules, so we will simply use the Maxwell-Boltzmann distribution here. So we will simply write W will be equal to n factorial pi I gi ni upon ni factorial. So as per this equation, n here it is given as 4 distinguishable, so total number of particles is equal to 4, so we will write it as 4 factorial. And this is in multiplication, so we'll first separate this G1 and G2. It is written as G1, it is degeneracy, and N1 particle upon N1 factorial multiplied by G2, here it will be the N2 upon N2 factorial. So this will be equal to 4 factorial. Now it is easy. Now we have to first put the value of degeneracy G1. So for E1 it is equal to 2, and similarly for G2 is equal to 3. So we will write it as 2, and N1 here it is simply telling about the number of microstates with 3 molecules in energy E1. That means 3 molecules are basically in the E1. So we will write it here, N1 will be simply equal to 3 upon 3 factorial as per this equation multiplied by. For the second, we know the degeneracy is equal to 3 and only one particle is present in now E2 energy level. So we will write it as N2 will be simply equal to 1 upon 1 factorial. So this comes out to be 4 factorial. It will be 8, and it will be 3 into 2 into 1, or you can say multiplied by 1 factorial, that is 1. So you can simply multiply the terms here. So it will be equal to 4. Now we will open this 4 factorial into 4 into 3 into 2 into 1. It will be 8 into 3, and we have 3 into 2 into 1. So this and this will go. It comes out to be 4 into 24. So it is equal to 96. So the answer for this question is 96 is the right answer. Similarly, a simple question was also asked. The tone symbol for the ground state ion is, this is P, This is 2s plus 1 value, this is j value. So it is term symbol. So the residual entropy of a crystal of a salt of this metal ion at 0 degree Kelvin, or simply 0 Kelvin. 0 Kelvin is the options were, first option was Kb ln of 1, second option was Kb ln of 3, third option was Kb ln of 5, and the fourth was Kb ln of 7. So first we know this simple relation that residual entropy is related to this by this equation Kb ln of W. What is W here? W is simply the total number of microstates. You can take this W as. And if a term symbol is given, here term symbol was given as 3p2, so this will be the j value and this will be the 2s plus 1 value. So basically this number of microstates for this case, if a term symbol is given, if it was simply on this, it is simply a term, but this is term symbol is given, so for this case we will write 2j plus 1. You have to remember this. So it will be equal to 2 multiplied by j value is simply 2 plus 1, so it will be 4 plus 1, which is simply equal to 5. So W is basically equal to 5. So we will simply write S will be equal to Kb ln of 5. So this was very simple question. So the answer is basically this third option. Like this, we will take one more question based on this microstatus so that you will understand what I was talking about. Suppose the total number of microstates for 1G term is, here you will see it is only term, not term symbol. So we have to calculate the total number of microstates. For this case, how to solve this? You have to use this equation 2s plus 1 into 2l plus 1. Here 2s plus 1 is given by 1 value, so you will write suppose 0, 1, 2, 3, 4, 5, so it will be S, P, D, F and G. So L value, here L value for this G will be equal to 4, So it will be simply equal to, in place of this we will introduce 1 because it is given here, multiplied by 2. From this equation L value is simply 4 plus 1. So it comes out to be, it will be simply 8 plus 1, which will be equal to 9. So the answer for this question was simply the 9. One more question we can take. This was basically asked in June 2016. The total number of microstates present in 3F term is. It is very simple. The options were, first option was 3, second was 21, third was 9, and the fourth option was 28. So I think you can do this question by your own. Okay, thank you.